Okay, we're going to look at another example of a double integral in rectangular coordinates. So this one's already set up for us, which sounds awesome. So we can just jump in and start doing integration. But about the time you start to do that, you should say, oh, wait, I really don't want to do that. So if I integrate with respect to y, x is being treated as a constant. I can pull that out front of this integral, not out front of the whole thing, but the one where I'm integrating with respect to y. But then I have to integrate cosine of y squared. This means, when this is written like this means cosine of y squared, by the way. So sometimes students are a little confused about what is squared. It's the y, whatever the square is right next to. Cosine of y squared integrating with respect to y. That, again, is a non-elementary integral. So if you're going to do that integral with respect to y, you have to write down a Taylor series, which converges to cosine of y squared, integrate the Taylor series, and then evaluate and then integrate the Taylor series again. So we'd really probably rather not do that if we can avoid it. So in this particular problem, there are some in the textbook homework which tell you to switch the order of integration. But you also should be able to recognize when you have an integral where you should do that without having to be told to do that. So the clue here is that this is a very difficult integral with respect to y. So it's maybe worth switching the order of integration to see if it might be easier to do this integral with respect to x first. So my piece of advice, though, is draw the picture. I always have a lot of students who try to do this, not a lot, I always have a few students who try to do this without drawing the picture, and guess what? They hardly ever get it correct. Okay, so draw the picture and then use the picture to help you reset up the integral with respect to x on the inner integral and go from there. All right, so I need to think about this region, so I'm going to pay attention to what this integral is telling me. It's telling me that on the inner integral, we enter the region at y equals x squared. And we leave the region at y equals 4. So when I go through the region in the direction of increasing y, since dy is on the inner integral, it's telling me that we're entering the region at y equals x squared and leaving at y equals 4. And after that integral has been set up with dy on the inner integral, if I collapse it in the y direction, I get a shadow of a region that goes from x equals 0 to 2. So it's important to pay attention to all those limits of integration and realize that it's not this entire region between this line and this parabola. It's really just the part where x goes from 0 to 2, so just this right half. Okay, so I've drawn the picture, draw the picture, and then use the picture to help you set up the integral in a different order. Okay, so if I now want to set this up with dx on the integral, I want to think about going through the region in the direction of increasing x. And I'm going to set the integral up that way. Okay, so I'm going to set this up with dx on the inner integral. I'm going to leave these outer limits of integration alone until I set up the inner limits of integration. My function, by the way, is continuous everywhere. So Fubini's theorem tells us I can do this. All right, so if I'm going to go through the region in the direction of increasing x, I'm going to enter at x equals 0, and I'm going to leave through the right half of that parabola. So I'm going to go from x equals 0 to, when I solve the equation of that parabola for x, technically I get x equals the plus or minus square root of y. So you want to be clear about which part it is that you're on. X equals the positive square root of y is the right half, where x is positive, and x equals the negative square root of y is the left half, where x is negative. So I just need the positive part for this one. If we'd been integrating on the other half, we would need the negative part. So x goes from 0 to the square root of y. And then now I want dy on the outer integral. So I want to think about collapsing that region back in the x direction. Look at the shadow of that region, what I have left on the y-axis there. So y will go from 0 to 4. Okay, so even without being told to switch the order of integration, we realize it's a very difficult integral with respect to y. We switch the order and hope that it's better with respect to x. This one is. All right, so let's go ahead and integrate with respect to x. So when I integrate with respect to x, this cosine of y squared is being held constant, so that will just come along. And then the integral of x with respect to x is 1/2 x squared. Again, my outer integral sign and differential do not disappear and then reappear later in the problem. They're there throughout the problem. I'm not doing anything with them, but they're just there waiting for me to be ready to deal with them. All right, these inner limits of integration were x values. Those are going from x equals 0 to square root of y. So I'm going to put these in place of x. Be sure you're putting in place of the correct variable here. That's why sometimes writing the x equals or y equals is helpful, so you don't put it in place of the wrong variable. All right, so I'm going to put this upper one in first in place of x. And so the square root of x, the quantity squared, square root of y, the quantity squared will just be y. And then when I put in 0, this will all just be 0, so that whole term will go away. So we're left with this. Okay, so now I need to finish this integration with respect to y, and just like the last problem we looked at in the last video, something nice happened after that first integration that makes this last integration a little bit easier to deal with. I'm going to do a U-substitution to finish this. Maybe these are U-substitutions that you can do in your head. I would let u equal y squared. Du is 2y dy. I don't have a 2y dy in there. I do have a y dy. So I'm going to get an extra 1/2. I have a 1/2 already here, but I'll get an extra 1/2 from the u substitution. All right, generally at about this point, even if students were not comfortable doing u substitutions in their head, at about this point, they start to decide maybe it's worth it to do them in their head. So maybe write out this much, or maybe just think it through, but to understand that because you don't have the 2y dy, you're going to end up dividing through by 2, so you're going to get an extra factor of 1/2 when you do that u substitution, in addition to the 1/2 that's there as well. Okay, so I'm just going to do this integral in my head. All right, so 1/2 that's here times the other 1/2 that I get from the other u substitution will be 1/4. The antiderivative of the cosine function is the sine function, and sine of u, where u is y squared. Okay, so if you can't do that antiderivative in your head, then write out the u substitution. But this is what I should get, and y is going to go from 0 to 4. My guess is by the time we get to the exam, many of you will be comfortable skipping some steps there. Key is skip steps, but do it correctly. Don't mess up the coefficient out front. Otherwise, it's not worth it to try to do that in your head. Just go ahead and write it out if you need to. Okay, so let's go ahead and finish this. So I have 1/4 sine of 16 minus 1/4 sine of 0. Sine of 0 is just 0, so that all is just 0. I don't need to write that. So 1/4 sine of 16, that's about as simplified as that can get. So that's 16 radians. That's sine of 16 radians is not a nice, pretty number. So you want to leave it like that in exact form. So again, just interpreting what this answer means, this is the total value of this function, thinking back to that definition of the definite integral when we built some things with Legos. Thinking about that, what this represents is the total value of this function on that region. So if I add up all the output values of this function at all the points, xy points that are in this region, this is what I get, right? Thinking about definite integrals as sums, total value of this function on this region. So all my xy points that are in this region, if I put them in here, add those function values up over the whole region, this is what I get. Okay, and that's helpful sometimes when you think about whether it makes sense that your answers should be positive, negative, or 0. We'll start to look at that in some future videos, thinking about whether we expect that our answers will be positive, negative, or 0. and then sometimes using that actually to create some shortcuts on some of the problems that we'll look at. All right, practice some right now though, some double integrals. Just practice some of these and make sure you can get through the mechanics, and then we'll get into some more concepts in the next few videos.